Welcome to Papers Walkthrough. Today we're going to be doing the Physics May-June 2023 Paper 4.2. Before we start, I would like to thank you for clicking and watching this walkthrough. I hope you enjoy it, and please subscribe and like if you enjoy the video. Thank you. Let's get going. Okay, so this paper bringing the threshold, I just remember for the A, it was 63% was what the threshold was for an A. It was a fairly difficult paper, but I hope we'll get through this very quickly. Question 1. State Newton's law of gravitation. As we know, Newton's law of gravitation, it's F is directly proportional to mm over r squared. So that is what we're going to write here. So force is directly proportional to the product of the point masses and is inversely proportional. Excuse my handwriting. Proportional to the square of the separation. Right, good. This reads force here. Alright, next question. If a satellite is in a circular orbit around the planet, the radius of the orbit is r and the period of the orbit is t. The planet is a uniform sphere. Use Newton's law of gravitation to show that r and t are related by the equation shown here, where m is the mass of the planet and g is gravitational constant. Alright, so what you have to understand for this question is that, remember it's saying the satellite is in a circular orbit. So for something to be in a circular orbit, first of all, it has to have been moving in a straight line, in a straight path, right? And then what happens? So this is what happens. So you have the Earth here, and then you have the satellite with a velocity in that direction. But then because it enters the Earth's gravitational field, it experiences a gravitational force downwards, like that. And then once that happens, it becomes a deflecting force. So it forces the satellite to orbit the planet, which is Earth. So we know from that illustration, we're going to know that the centripetal force is provided by the gravitational force. So that's where we start our equation. So we say force gravitational provides the force centripetal, right? And we know that we can see in our equation here that we have T. The variation for the centripetal force, that is T, has omega in it, right? And omega is equal to 2 pi over T, like that. So then we write our equation, which is m, which is gmm over r squared, which is equal to, this is equal to m r omega squared, right? And our omega is 2 pi t. If we square that, we're going to get 4 pi squared over t squared, right? And then we can cancel out that. Then we have our gmm over r squared is equal to r multiplied by 4 pi squared over t squared. Then if we multiply this by the t squared and the r squared, right? I'm just going to rub this out for more space. I'm going to take this off for more space, right? We're going to have that. So multiply by t squared and r squared, or take t to that side and take r to that side. Just like that, we're going to have the GMT squared is equal to 4 pi squared r cubed, okay? And we've shown that, right? So the main idea, remember, is just that the centripetal force comes from the gravitational force. It is the one that causes the centripetal force because of the pull, which forces the satellite to go into orbit. All right, next question. C. The Earth may be considered to be a uniform sphere of mass 5.98 by 10 to the 24 kgs and a radius 6.37 by 10 to the 6 meters. A geostationary satellite is in orbit around the Earth. Use the expression in B to determine the height of the satellite above the Earth's surface. Okay, so the illustration for this question is we have the Earth, right? And this is the surface, the outer line is the surface, and we have an orbit, and we have a satellite in that orbit, right? We have a satellite in that orbit, the geostationary satellite, right? So the question here is saying determine the height of the satellite above the Earth's surface. And the R that we have for equation, remember, that provides the centripetal force, is from the center of the Earth all the way out. This is what R is. This is the value of R that we have from this equation, yeah? From this equation. Since we're going to use it, remember it says use the expression in B. So we're going to use this expression here to calculate C, right? So what we want, and we know that from this equation, we've been given the radius of the Earth, which is 6.37, right? We know that from here all the way to there, that is going to be the radius of the Earth. I'm just going to label it RE, right? We want the height above the Earth's surface, which is this part here. I'm just going to label it H, like that. So we know that H is equal to R minus the radius of the Earth, just like that. And we know how to calculate R. We just rearrange this formula. And when we do so, we get our R is equal to the cube root of GMT squared over 4 pi squared. Just like that. This is G. Then we substitute in the values that we have. We have the cube root 6.67 for the value of G by 10 to the negative 11. 10 to the negative 11 multiplied by the mass of the Earth, which is 5.98 by 10 to the 24 multiplied by the period. Remember, the period of rotation for a geostationary satellite is the same as the Earth's period of rotation. And you know that the Earth's period of rotation is 24 hours, a day, a whole day. So which is 24, but we want it in seconds. So we multiply by 60, that puts it in minutes, multiply by another 60, that puts it in seconds. Then we square that. Then all of this is over 4 pi squared. Right, then you just put that in your calculator. When you do that, you're going to get your R is 4.2, right, by 10 to the 7 meters. Why did I use two significant figures? This is another issue that I need to address. You see, for the third mark, if your answer is not exactly the same as in the mark scheme, then you're not going to get the third mark. You have to watch your significant figures. So why did I use 4.2 instead of 4.23? Because remember, we use our data. Our data, yeah, the lowest degree of accuracy at figure at two significant figures. Remember, we use 24 and 60 and 60, right? So that limits the accuracy of our answer. Our answer cannot be more accurate than the data that we have. I don't know if that makes sense. We have two significant figures for the 24, the 60, and the 60. So this limits our accuracy. If we had another data value that had one significant figure, then our answer would have to have one significant figure, right? But normally it's two significant figures and three significant figures. You see, as we go through this paper, I'll show you what I mean. All right, so we have our R is 4.2 by 10 to the 7 meters. Now we want h. We know that h is equal to, from our equation here, down here, we know that h is equal to r minus the radius of the earth. So we go 4.2 by 10 to the 7 minus 6.37 multiplied by 10 to the 6. Then we subtract that. Right. When we do that, we get our answer. Remember, the limiting value for significant figures is the 4.2. Right? It is the lowest degree of accuracy, this value here. Okay, so our answer is going to be 3.6 by 10 to the 7 meters. All right. Next question. D. Another satellite is in a circular orbit around the Earth with the same orbital radius and period as the satellite in C. Calculate the angular speed of this satellite in this orbit. Give a unit for your answer. Alright, so we know that the angular speed, the formula for that, everyone knows that it's omega is equals to 2 pi over t, right? So this means it's supposed to be pi 2 pi, like that, over t. And we know that the period is the 24 hours, since it is the same period as in C. Then we just divide by that. But then we have to turn 24 hours to seconds, convert it to seconds. So it's 24 multiplied by 60, that turns it to minutes. Then multiply by another 60, that turns it to seconds. Right, and our answer is going to have two significant figures because of our limiting values, the 24, 60, and 60. And our answer will be 7.3 if you plug that in the calculator. 7.3 to the negative 5. And our unit for angular speed is rad per second. Radians per second. Okay. Just like that. Right, 7.3. Change the negative 5. Just like that. Next question. Despite having the same orbital period, the orbit of this satellite is not geostationary. Suggest two ways in which the orbit of the satellite could be different from the orbit of the satellite in C. Alright. So for a satellite to be in a geostationary, or to be geostationary, remember the conditions. We have one. The Earth rotates from west to east. So the satellite is to follow that pattern. So west to east rotation to east. Right? And then second condition, um second condition, the period has to be the same. So the Earth's period is 24 hours, same as the satellite. So it has to have same period. And then the third one, it has to be in an equatorial or region, an equatorial orbit. An equatorial orbit. So it has to be in equatorial orbit, like that. Right. So we already know that this satellite has the same orbital period there, right there. So that is correct. That's fine. So a different now, it's saying suggest two ways in which it would be different. So the only way here, one would rotate from, oh, that's the wrong word, orbit from east to west, right? And then it's not in an equatorial orbit, not in equatorial orbit. Okay, that should earn you 2 marks. All right, next question. Question 2. state what is meant by an ideal gas. Okay, so an ideal gas is a gas that obeys the equation it's a gas that obeys the equation PV is directly proportional to T. I'm sure if you would also write PV over T is directly proportional to constant, that should also get you your marks. But Cambridge in this case, they wanted PV is directly proportional to T. Alright, and then you need to state, remember the special condition for T, right? T is has to be an absolute temperature, has to be the absolute temperature, not in degrees, but in kelvins. Right, so, comma, where T, absolute temperature. Temperature. Take the temperature in degrees Celsius for an absolute zero. Okay, so the formula to convert from degrees to kelvins, it's theta representing degrees is equal to K representing the kelvins minus 273.15, right? And we know that at absolute zero, K is equal to zero. It's 0 kelvins, where the gas molecules completely stop. Okay, sorry, there was a mistake that happened. So for question 2, state what is meant by an ideal gas. An ideal gas, it is a gas that obeys the equation PV is directly proportional to T, where T is the absolute temperature. You have to state what T is so that you get that second mark. You can also state PV over T is directly proportional to constant. I'm sure you should also get that mark as well. Right. Then for the second part, state the temperature in degrees Celsius of absolute zero. Right. So here you can use the formula theta is equals to K minus 273.15. And then when you substitute your value, when we know that for absolute zero, K is equal to zero, you can substitute in your K, then you're going to get your theta, which is in degrees Celsius. It's negative 273.15. And then for this question, yeah, it says, a sealed gas vessel contains a mass of 0.42 by 10, 442 kgs of an ideal gas at 227 degrees Celsius. The pressure of the gas is 1.37 by 10 to the 5 pascals, and the volume of the gas is 0.640 cubic meters. So the way you calculate this is, let me just show you. I didn't record this part, right? Let me show you how you get it done. Okay. Okay. So what you actually do is we use the equation PV is equal to NKT. But I want to show you where this equation comes from. So remember you have your classic PV is equal to nRT, right? But N is equal to number of moles over the Avogadro constant, right? Then you just substitute it into that equation. Now you have PV is equal to N over NA RT, like that. And then this part here is the Boltzmann constant, K, right, which is equal to R over NA, the Avogadro's number, right? That's how you get your PV. So it becomes PV is equals to NKT, just like that. All right, so that's how you do that part. So now let me do the calculation. Just wanted to show you where you get that equation from. Okay, let me do the calculation now to get the number of molecules. Remember, moles and molecules are not the same. Remember that. So N is equal to PV over KT. Then we substitute in the values that we have. We have 1.37 by 10 to the 5 multiplied by the volume all over the Boltzmann constant multiplied by the temperature. The temperature, remember, it has to be the absolute temperature. So we use our formula, which is theta equal to K minus 273. Right. In this case, our theta is equal to 227. So we can substitute in, then add 273 to the both sides. We'll get our K as 500 kelvins. So that's our temperature now. That is what we're going to use. And then the Boltzmann constant. For the Boltzmann constant, we have it. It's in the data booklet. There it is. It's right here. Right here. 1.38 by 10 to the negative 23. That's the value that we need here. 38 by 10 to the negative 23. Then we plug that into our calculator. Since all of our values are 3 sig figs, you can use and then also since our answer has an accuracy of 3 sig figs, I mean since our data has an accuracy of 3 sig figs, right, we can also use that for our answer. We can put it to 3 significant figures. If you put it to 2 significant figures, you're going to get 2 marks at most. They won't give you the 3rd mark. So make sure you watch for your number of significant figures. Multiply by 10 to 25. Right, that is the number of molecules. Okay, the mass of one molecule of the gas, think about it. We know that the number of molecules are 1.27 by 10 to the 25, right? And we know that the mass of the gas, we have it right here. Okay, it's 0. So we know that mass is equal to 0.0424 kgs. And N, number of molecules, equals to 1.27 by 10 to the 25, right? And we want mass per molecule, so we just divide that, right? The mass of one molecule, mass per molecule, 1.27 10 to the 25, just like that. And we have our answer in 3 significant figures. Since our data is in 3 significant figures, 3.34 by 10 to the negative 28 kgs. And then we just plug that in. Okay, good. Next question. The root mean square speed of the molecules of the gas. Okay, so for this part, we're going to employ the equation that we're given in the data booklet, which is P equal to 1/3 multiplied by N M C squared over V. Alright, and we want to get the C squared, the mean square speed, right? The mean square speed C, right? Then we're going to root it to get the RMS. Multiply the 3 to that side with 3 and V right there, divided by NM, right? Then when we square both sides, we have the RMS. Okay, this equation is given in the data booklet. If you check the data booklet, it's right there. Okay, data booklet, the data that you're given at the start. Okay, it's right here. Where's this equation? Right, there we go. It's right there. Ratio of an ideal gas. Okay. Alright. So when you square that, now you have the RMS. This is equal to the RMS, this part here. This part is equal to the RMS value. We know that, remember, NM, number of molecules multiplied by mass of one molecule. Remember, the M here is mass of one molecule. And then multiplied by the total number of molecules. That gives us the mass of the gas. And we do have the mass of the gas. So we can just substitute those values in. 3 multiplied by the pressure. The pressure 1.37 by 10 to the 5. 1.37 by 10 to the 5 multiplied by the volume, like that. Then we're going to divide by the mass of the gas, 0.0424. Right, just like that. This is the mass of the gas that we have. All right, and then when we plug it into the calculator, which means just plug it into the calculator real quick. 3.37 10 to the 5 multiplied by 0.604. Okay, good. Then I'm going to put it to 3 significant figures. Remember the accuracy of my values. You don't usually consider the constant, because if it's a constant, then its accuracy is to the infinity, because it's 3.00000. So it's fine. So you usually consider the other numbers, the other data that you have. So you get 290 meters per second squared. Then you just put it right there. I mean, 2,490. Sorry, excuse me. Right. Next question. The gas in B is now cooled gradually to absolute zero. On fig 2.1, sketch the variation with thermodynamic temperature T of the RMS speed of the molecules. So we want the relationship between the RMS, right, and T. We want what relationship is there, so that you know the shape of the graph. So what we can do, we can get that from the equation for the kinetic energy of a gas, right? We know that the kinetic energy of the gas equal to half m, right, mean square speed, like that. Where do we get this from? Let me show you. Let me show you how you derive to get it. Remember, this doesn't have the t. What is the t? Is then equated to 3 over 2 kt, like that. Okay. Let me show you where you get how you get that equation, how you derive that equation. So remember, we have our PV is equal to nkt, right? That's the equation 1 that we have. Then we also have an equation 2. Our PV is equal to, well, it's actually our pressure first, 1/3 nmc squared, like that, over the volume. All right. Right. Then you multiply the v to that side, so that cancels out. That goes away. This v, yeah, goes away when you multiply it, so that you have the PV, right, is equal to that. Then you can equate this. So now you have your 1/3 nmc squared equal to nkt. You can cancel out the n's, multiply both sides by 3. Now we have mc equal to 3 kt. And look at this. This is analogous. Remember, kinetic energy, formula for kinetic energy that we know, it's equal to half mv squared. Remember that. And if we divide that by 2, that becomes the kinetic energy of the molecules of the gas. We divide that by 2, we get our half m mean square speed, 3 over 2 kt, like that, right? And we know that this is equal to the kinetic energy of the gas. So kinetic energy, therefore kinetic energy must also be equal to, since this is equal to that, 3 over 2 kt, right? So now we have the relationship that we want. Relationship that we want really is this. It's from this equation here, right? if we strip all of this and make all of this it's if we make all of this here is constants, all of this is just constants, right? Our relationship that we have is c squared is directly proportional to t, right? That's all we wanted. But remember, this is just the mean square speed. I mean, this is just the mean square speed, this here. So we want the root mean square speed. We just root both sides. And now we have r, m is directly proportional to root t. That's our relationship, right? And remember, we have the RMS here and the temperature right there. And if you know the graph of y equal to x, this is what it looks like. So if we're going to have like that. That is what the graph looks like. There we go. Okay. All right. Move on to the next question. Question 3. Say the first law of thermodynamics. Identify the meaning of any symbols you use. All right. So what you do here for this particular question, the first law of thermodynamics is delta U equal to Q, energy supplied, plus the work done on the system, right? That's what you do. So then you can just explain the symbols. Delta U, change in internal energy. And then Q, heat supplied by heating. And then M, and then W, double V, right? There's the work done on the gas. Remember, work done by gas and on the gas is different. So I'll explain what that means for this next question. B. State the state of an ideal gas is continuously changed according to the cycle A, B, C, D is shown in Fig 3.1. Okay, so it's saying complete the table 3.1 for the changes A to B and B to C by placing two ticks in each row. Table 3.1, test table 3. Okay, so the best way to think about this is we have the equation, right? I think the best way to think about this question is just draw your diagrams, right? You can draw your diagram. You have your vessel, and that's the plunger right there. And you have the gas particles inside. Okay. So when you push the plunger down, you do work on the gas. You do work on the gas, right? So it's positive. So this is compressing. So compression, right? When the gas does work, it expands, therefore pushing the plunger up. That is minus W. It's an expansion. Expansion. Right? That's the best way to answer these questions, really. Okay. So if you look at the diagram now, it's saying here in the table, it's saying change from A to B, B to C. So change in internal energy. Is it a decrease and no change in increase? Work done on gas, is it negative, zero, positive? Okay. So now, if you write your equation of first law of thermodynamics. You have your Q plus your work done. Right. So let's think about it. Look at the graph here. This graph here. From A to B, it is this route here. Right there. What's happening? We are changing volume at constant pressure. So we are changing volume at constant pressure. So, and how are we changing? It's decreasing. So we are doing work on the gas, right? When we compress, remember, when we compress this, right, the volume decreases, right? And remember, the work done on the gas is equal to the pressure multiplied by the change in volume. This is the equation, right? So since we're doing work on the gas, it is positive, right? So we tick in that box, right? Now think about it. If what happens each time you have a balloon that is full of air, and then you try to compress it, right? What happens? You see, the air inside tends to build up on one side, right? Why? Because you're increasing the pressure by compressing, by trying to reduce the volume. So now, if you're reducing the volume, naturally the pressure should go up. Remember Boyle's law. Its pressure is inversely proportional to volume. Boyle's law. If you remember Boyle's law. Boyle's law. Right? So as the volume decreases, the pressure should increase. Right? But what is happening in our case? The pressure is staying constant. It's staying constant. So how can it stay constant? The only way that is logical, that will bring a logical answer is the gas is being cooled down. It's losing heat energy. All right. So the temperature decreases. And we know that once the temperature decreases, the potential energy of the gas decreases. The potential energy of the gas is linked to the internal energy. Because remember, the internal energy, when it's on, right, on its own, it is just the total potential energy plus total kinetic energy of the molecules, right? And this is decreasing. Therefore, this decreases. And therefore, it is a decrease. Right? I hope that makes sense. If you use Boyle's law, and there's also Charles' law, right? There's Charles' law. Charles' law may explain this better. Remember, it says the volume at constant pressure is directly proportional to T, right? So you can use Charles' law, Boyle's law, and the pressure law. They will help you answer this question. And since they are proportional, remember, volume is decreasing, therefore temperature should decrease. Once temperature decreases, that means internal energy decreases. All right, I hope that makes sense. If it doesn't make sense, just comment below the question. I'll explain it further to you. Okay. And then B to C. So what's happening for B to C? From B to C here, we can see that B to C is this part. The pressure is increasing at constant volume. So you can see it's at constant volume. It's at one value of the volume. Using our equation here, this equation right there, right? This equation right here that I've marked in green, we know that it's pressure multiplied by the volume, by a change in volume. So if there's no change in volume, that means if the change in volume is equal to 0, that's P times 0. So therefore the work done is 0. Alright, so the work done on the gas here, in this case, is equal to 0. I'm going to mark that in green right there. And then the change in internal energy. Since we're not told whether there's a change in the thermal energy, in the heat supplied in Q, we know that the internal energy change is equal to no change, right? And then that's how you fill that table. It's clear. Next question. Use the first law of thermodynamics to describe and explain the energy transfers associated with the one complete cycle, A, B, C, D, A. Okay, so we're going to use the first law of thermodynamics to describe and explain the energy transfers, right, of this cycle here. See, it's a complete cycle. Okay, so it starts from A, right there, then it goes to B, to C, to D, then back to A. Right, so it's a complete cycle. It's a complete cycle. So what that means, right off the bat, it means that the change in thermal energy, in internal energy, is equal to 0. So we write overall the change in internal energy, we could just write delta U equal to 0. That's one point that we can note from the graph. And then if we look at the graph again, so we're just looking at whatever we can comment for the graph. Right, look, from B to C here, the pressure increases. How could the pressure increase when we have constant volume? The pressure law. Remember, the pressure law states the pressure is directly proportional to the temperature at constant volume. Right, so pressure increase, that means temperature increase. How can the temperature increase when there's no work being done on the gas? It is being heated. Okay, it is being heated. So for B to C, heat must have been supplied. To increase the pressure. Right. That's one thing that we can comment. And then third thing that we can comment. If you look at CD and AB, right? CD and AB. I'm just going to rub out some of this, all of this, yeah? If you look at CD, and AB, what can you notice? Look at the equation for the work done. That is on the green star. Work is equal to pressure times change in volume. So for CD, the change in volume is the same. Since it's a rectangle, it's the same. But look at the pressure. Pressure, just write that in red. Pressure for CD is greater than pressure for BA, for AB, like that. So that means the work for CD is greater than the work done by gas is greater than work done on gas. So this is work done by gas, it expands. This is work done on gas, it is compressed, right? Okay, so that is what we're going to write here. Okay, work done on gas, right, at CD is greater. You can just write is greater. I'm just going to use the greater than sign here. Than work done by gas AB. Right, there you go. Those are your 3 points that should earn you your 3 marks. Okay, number 4. A small steel sphere is oscillating vertically on the end of a spring, as shown in Fig 4.1. They are the oscillation, the spring, and the steel ball. The velocity v of the sphere varies with displacement x from its equilibrium position according to this equation there, where v is in centimeters per second and x is in centimeters. Calculate the frequency of the oscillation. Okay, So if you look at this equation, this is exactly the equation that we get for calculating the velocity in simple harmonic motion. It is exactly this equation right here. Right. So we know that whatever value is here is going to be the angular frequency or angular velocity, and then the value here is going to be the amplitude, and this is just going to be the displacement. All right. So if we go back to our equation, we know that the angular frequency right there is going to be 9.7. Right. So, and then we know that that is equal to 2 pi f, right, from the formula for angular frequency. Then we get f of f is equal to 9.7 divided by 2 pi. Right. And it's going to have significant figure, it's going to be 1.5. That's right. That's our answer. Simple. Simple like that. Show that the amplitude of the oscillations is 3.4. Remember, it's amplitude squared from our equation here. Look, it's amplitude squared. So that means our 11.6 must have been squared. A value must have been squared to get 11.6. So we know that a value of x was squared to give us 11.6. X naught was squared to give us 11.6. So to get our x naught, which is our amplitude, we just root that 11.36, and we're going to get 3.4, right, centimeters. And that's it. We've shown that equation, that question. Part 3. Calculate the maximum acceleration a naught of the sphere. All right. So when do we have maximum acceleration? So remember, as this oscillates, it's going to have a maximum extension, right? And it's going to have a minimum extension where the ball is somewhere here, and this is sort of like the midline, which is given there, right? So when that happens, remember our equation, simple harmonic motion equation, its acceleration equal to minus omega squared x, right? So as you can see, acceleration is going to be maximum. Acceleration A will be maximum when the amplitude is maximum. All right. When the displacement from the equilibrium position is maximum. And that happens, maximum displacement from equilibrium point is the amplitude. It is the amplitude. Okay. Amplitude like that. Okay. So we know that A naught equal to omega squared amplitude. You get our A naught negative. In this case, we can ignore it. The calculation 1.5 by 10 to the squared. So you can ignore the negative sign for this calculation. Remember, it just shows that the acceleration is always directed towards the equilibrium position. That is what this negative sign is for. So we can ignore it for calculations. It doesn't really matter. You can actually do away with it when you put the numbers right there, multiplied by the amplitude, which is 3.4. Remember, our answer, watch, it's in meters per second squared, but our value is in centimeters. So we have to change that to meters. And we do that by multiplying by 10 to the negative 2, or by dividing by 100. That makes sense. If you divide 3.4 centimeters by 100 meters per centimeter, you see, 100 centimeters per meter. Remember, one meter is equal to 100 centimeters. 100 centimeters per meter. If you do the cancellation of units, that goes away and then that goes on top. Then you have a 3.4 multiplied by 10 to the negative 2 meter. That's all. Then you multiply that 1.5 squared multiplied by 3.4 by 10 to the negative 2. And you got your answer is my bad. Look at what I did. This is the wrong value for this is the frequency. I want the angular frequency. Right. It's 9.7. Like that. And then when I do the calculation, I get my 3.2. Watch for the sig figs. For the number of significant figures, 3.2 meters per second. All right. Then B. On fig 4.2 sketch a variation, or with x of the acceleration a of the sphere. Remember, our equation for S.H.M, simple harmonic motion, is a equal to negative omega squared x. This is the displacement, this is the gradient, and it is a negative. It's a negative gradient. All right. And then we have the acceleration, maximum acceleration a naught. Remember, maximum acceleration occurs at maximum amplitude. What is our maximum amplitude? Our maximum amplitude occurs at 3.4 centimeters. So that's right there. And 3, 2, 4 right there. Then you take it up as well. Okay. Right. I'm trying to trace this line with dots, but it's not that accurate because on the screen it's very difficult to be that accurate. But I'm sure on paper you can you can trace these dots with your ruler. Okay. Remember there's a negative gradient. Negative gradient. And your graph can't go past. You draw a line for the graph. Okay. All right. Good. Your line cannot go past this like that. It cannot. Why? Because the maximum amplitude is 3.4 and it cannot go all the way there. Because then now you have this region here and you have this region here. That is wrong. If you put that, if your line extends beyond this point here, and this point, then you're not going to get, you're going to get 1 mark deducted. So you don't want to do that. You want to make sure your graph is as accurate as possible. Yeah. All right, there we go. Okay. Our next question, excuse me, is this. Is this Gibraltar? All right. Describe without calculation the interchange between the potential energy and the kinetic energy of the oscillation. I don't know if you remember the graph, the kinetic and potential energy. It was something like this. Right? And then this is the maximum. This was the maximum energy. And then you have here. It's not that accurate. It's supposed to be touching that. Yeah, that's better. It's supposed to be right on the axis right there. Okay, so remember the kinetic energy. It is this is the sine graph, right? This is the kinetic energy, and then this is the potential energy, EP, right? And this is the displacement, X, right? And here we have maximum energy, maximum total energy. Right. So what happens is, this is what we are supposed to explain. So it's the oscillation, when the oscillation is at maximum, this is where the amplitudes are, negative amplitude and the positive amplitude. This is where it is zero, displacement. So at maximum amplitude, right, we have the kinetic energy to be zero, as you can see from this graph. So we write that it max amplitude ek is equal to 0. Then the converse is also true. X is equal to 0, right? Where x is the displacement. What is happening? Ek, we can explain Ek here is kinetic energy. Don't use symbols without explaining them. Cambridge might not know what you mean. So if you're going to use a symbol, make sure you explain it, or you just have to write it in full. It zero displacement, right? The potential energy. So you can see from the graph right there. From the graph right there, it is maximum, equal to max, right? Okay. Wait a minute. I confused the way I explained it. It's actually the opposite. It's that it's kinetic energy. Look here, at maximum displacement, the kinetic energy is 0. The kinetic energy is 0. All right. Kinetic energy is 0, and here, right, it's 0 displacement. Potential energy is maximum. Just like that. Right. That's what you put, and then you just indicate that total energy at any point is equal to the kinetic energy plus the potential energy. And you explain your symbols that Ek means kinetic energy and Ep it represents potential energy, right? So that's what you do. Okay, and then here you can just write as well. I'll show you. You can write and Ep equal to max, then there and Ek equal to 0. And you can even draw the diagram. That will make it easy. I'm sure you get the 3 marks if you want. They appreciate you when you show illustrations of what you write in your answers. They really do appreciate that. Question 5. Two capacitors A and B are connected into the circuit shown in Fig 5.1. Capacitor A is capacitance C and capacitor B is capacitance 3C. The electromotive force EMF of the cell is V. Two-way switch S is initially at position X and a capacitor B is initially uncharged. State in terms of V and C expressions for the initial charge QA on the plates of a capacitor. So we know the formula for charge is CV, right? So for QA, it's going to be the capacitance is C and the voltage is V. The electromotive force is V. So just write the CV. The initial energy EA stored in the capacitor. We know that energy EA is equal to QA multiplied by C. Multiplied by V, right? That is the equation that we have for energy. But then it says in terms of V and C, so we have to substitute QA with CV. And it's half. And you get our EA is half CV squared. Half CV squared. Just like that. And then those are our answers. B1. The two-way switch S is now moved to position Y. Study and explain what happens to charge that was initially in place on the place of a capacitor A. So what happens is when you change this switch from here, if you remove it here, right, we take it off. It's no longer connected on X, right? Then we connect it on Y. Now we've connected it here, right? The charge will move from the plates of this capacitor into charge B. When will that stop? When VA becomes to the potential at A becomes equal to the potential at B. That is when charge stop flowing, when current is equal to 0. Okay, so that is what we're going to write for answer. Okay, so charge flows from capacitor A to capacitor B. Right. And this will happen until VA becomes equal to VB. Just like that. And that should be fine. And you can explain your symbols if you want. That VA is the potential at A, at capacitor A, of capacitor A, and VB is the PD of capacitor B after the discharge capacitor A. Show that the final potential PD VB cross capacitor B is given by VB equals to V over 4. Okay, so the first reasoning is that principle of conservation of charge. Of conservation of charge. The fact that charge cannot be created, neither can it be lost. Sorry. Of charge. Like that. Okay. Principle of conservation of charge. And then in this case, they wanted you to also state the condition that VA becomes equal to VB. So just to state these two for your next paper, right? Make sure when you write, state these two. Because sometimes the thing is, you know the answer and your answer is probably correct. But sometimes it's not what Cambridge is looking for. So sometimes you've got to give them what you're looking for. And you can see this pattern as you do more and more papers. It's difficult to grasp, but as you continue to study and as you continue to do these papers and look at their mark schemes, you actually see a pattern. So what I have noticed, the best thing to do is if you know certain conditions, just write all of them. Write all of them. They'll just pick what they want from what you've written. So yeah, initial charge. Remember from this diagram, this was right there. This was connected right there, and A charge, the battery charged cell charged capacitor A, right, only, not capacitor B, because it wasn't connected. So all of the charge accumulation went on capacitor A. So we're going to say initial charge equal to CV, right? Then our final charge, right, is going to be equal to the total capacitance, right? The total capacitance and the total voltage. So we calculate that by saying CA VA plus CB VB. But we know that VA is equal to VB, remember, from this, right? After capacitor A is charged capacitor B, right? They'll become equal, right? The potential. That is the only way the charging will stop. Okay. And we know that the capacitance for A is just C. So we have VB here. We've substituted VA for P. And we know that the total capacitance for capacitor B is equal to 3C VB. Then that will equal 4C VB, right? And we know that initial charge is to be equal to final charge. Remember our first condition right there, principle of conservation of charge. And then we just equate that equation 1 and that equation 2. So if CV is equal to 4CVB, you can cancel out the C's, and VB, if we rearrange, we're going to get our VB as V over 4 divided by 4 both sides. And we've shown that VB is equal to a quarter of V. Next question. Determine an expression in terms of V and C for the decrease E in total energy that is stored in capacitors as a result of the change of the position of the switch. Remember, some of the energy is lost due to the resistance in the conductors. That is the delta E. And you know that delta E, right, is equal to initial energy minus final energy, right? That will give us the difference, right? So for the initial energy, remember we only charged capacitor A. So that was half CV squared, right? Then minus half. Right, now we want the total capacitance, right, for the final energy that is stored in both capacitors. So for that, if you look at the diagram again, you're connected. For us to determine the capacitance, remember there is parallel addition and series addition. So the capacitors in this case, if you look at it, they are connected in parallel. If you do that, you can actually plug a voltmeter and measure the PD between them, which is the same. Remember, that's why we're saying it's the same, right? Which should be the same. We can actually measure the PD, right, using a voltmeter. So you can see they are in parallel from this diagram. So if they're in parallel, we just add the total capacitance is this is C and this is 3C. So the total capacitance becomes just 4C, right? Okay. And then the PD between them, remember it's VB is equal to VA, right? VB is equal to VA, which is equal to V over 4. Remember from this part, here, VB is equal to V over 4. Okay, so we can plug that in now. Multiplied by total capacitance, which is 4C, multiplied by total, the new value for V, which is VB is equal to VA, which is equal to V over 4. Then we square that. Then our expression becomes half CV squared minus 1 over 8 CV squared, and then we get our 3 over 8 CV squared. In this case, you could also write it as 0.375 CV squared, but I'm just going to leave it as 3 over 8 CV squared. Okay. All right. Question 6. A heavy aluminum disc has a radius of 0.36 meters. The disc rotates with the wheels of a vehicle and forms part of an electromagnetic braking system on the vehicle. In order to activate the braking system, a uniform magnetic field or flux density 0.17 teslas is switched on. This magnetic field is perpendicular to the plane of rotation of the disc as shown in Fig 1.6. Okay. So we have the direction of the magnetic field going from left to right. Rotation is into page and then with the rim, exo, and everything. So question A, define magnetic flux. Right. So flux is literally just the amount of magnetism, right? And to get the amount of magnetism passing through a unity area, right? So it's literally just phi is equals to BA, right? And that's the answer. That is what we're going to write. So for the magnetic flux, product of the flux density, which is B, and the cross sectional area placed perpendicular to the field or to the magnetic field. Like that. And that's your answer. Product of the flux density B and this is and the cross-sectional area, right, placed perpendicular, which is the direction of the magnetic field. Okay. Direction, that says direction of the magnetic field. I just don't have space here. Right. Product. So a magnetic flux, it is the product, the flux density of the magnetic flux density B, right, and the cross-sectional area placed perpendicular to the direction of the magnet. Remember, you just don't place this area anyway. Remember, as you can see, the cross-sectional area, especially for this diagram, this cross-sectional area, it is at 90 degrees with the field. As you can see, it's at 90 degrees with the field. Right, okay. All right. Next question. Calculate the magnetic flux through the disk. We're going to employ our formula. Phi equal to BA, which is equal to B multiplied by pi r squared. Right, then we have our given our magnetic flux density. Pi by the radius is given, the disk squared, and just verify with the data. Okay, then we plug that in the calculator, and our data is going to be to 2 sig figs 6.9 by 10 to the -2. And then our unit is going to be in Weber, unit for magnetic flux. Okay. What B? The disk is rotating at a rate of 25 revolutions per second. Calculate the magnitude of the electromotive force induced between the axle and the rim of the disk. So the formula, right, from Faraday's law of induction, it is equal to E is equal to change in magnetic flux, rate of change of magnetic flux, like that. Okay. And you know that it's 25 revolutions per second, right? Which is the frequency. So to get the time, we just divide that by 1. Okay. Uh, so that with the flex, remember 25 It's rev per sec. This is the frequency. Remember the relationship between frequency and time. So one and period, it's that, or time. It is F is equal to 1 over T. Now, so to get the T, we just say 1 over 25. So if you plug that in with the answer that we got for our flux, magnetic flux over 1 over 25, which is essentially just multiplying by 25. You get your answer to T sig figs. This to be 2 sig figs, 1.7 phi. Here we go. C. The EXO and the rim are connected to an external circuit that enables the battery, the energy of the rotation of the disk to be stored for future use. The direction of rotation is shown in Fig 6.1. Use Lenz's law of electromagnetic induction. Determine whether the current in the disk is from the rim, the EXO, or from the EXO to the rim. Alright, so Lenz's law. That's the first thing that's what I'm going to state since he's saying use Lenz's law. Lenz's law. Direction of induced current or EMF is always such that it opposes the change causing it. Right, that's Lenz's law. Alright, so now we need to state how it applies to this particular problem. Okay, so they're saying the EXO and the rim are connected to an external circuit. Alright, let me show you what they're saying. They're saying that the rim right there, then the EXO, right, it's now connected to perhaps an external circuit, and then perhaps to a battery, right? But actually, to not confuse you, let's just do this. It's connected to a circuit, just like that. That's the best way not to confuse you. Okay. So now remember the principle of electromagnetic induction. When a conductor spins or rotates in a changing magnetic field, a current is induced in it. Right. So in this case, we're using Lenz's law. Right. So what happens is the current, first of all, is going to be perpendicular to the direction of the field. All right. So current is going to be from there to there. We just need to determine the direction, whether it's up or down. Okay, that's the first thing. Now we know that from Lenz's law, the direction of the induced current is always such that it opposes the change causing it. So the rotation of the disk is into page. So from Lenz's law, the current should produce a magnetic field that opposes the magnetic field that is causing that current. No, does that make sense? So we have a magnetic field here, right? We have this magnetic field going in that direction, right? So now, and then we have a conductor that is rotating in that magnetic field. By the principle of electromagnetic induction, a current is induced in that conductor, right? But that current opposes the change that is causing it. And the change that is part of the characteristics of the change that is causing it is that the magnetic field is from left, right? As you can see, it's from left So it's like there's a north pole here, and a south pole here, right? Something like that. Remember, because of the direction of the field lines. So we need to produce the current that is produced. Remember, when a current flows through a conductor, it also produces its own magnetic field. So let's say we have a conductor, and there's a current in it, in that conductor. It will produce a magnetic field, and the direction will determine using the thumb rule, the right hand thumb rule, right? So in this case, the direction of the field is going to be like that. It's going to be like that. If we curl our fingers, direction of the field that is caused by the current carrying conductor. Okay, that's the direction of the field. If we use our right hand thumb rule, right? Okay. So the direction of the current that is going to be produced in this particular um, in the disk, the direction of the current that is going to be produced in the disk is going to be such that it produces a magnetic field that is opposing this magnetic field that we have, that opposes this particular magnetic field. So if we use our left hand rule, in this case we can just use the fact that the rotation of the disk is into page. So our force is to oppose that. So it's going to be out of the page. If we use our left hand rule, we will see that the direction for a field, direction or for a force be out of page, and then the direction for our, so this is the left hand. So you have your first finger pointing in that direction, you have your middle finger down, and then you have your thumb pointing to this side. So our force is going to be in this direction, right? Out of page. It's going to be out of page like that. Our force is going to be out of page like that, since the rotation is into page. Okay, so this is our force out of page. Okay, this is just the rotation into page. Okay, just like that. And then I'm going to rub this out. Okay, so when we do that, we see that this is our first finger. We see that this is the current. Our first finger denotes the magnetic field, right? Uh, and our thumb, the force. So then our current, see, it's going down. And therefore, we've solved our problem. The current comes from the rim and goes to the axle, just like that. If this question still doesn't make sense, just comment below. I'm going to put my email. You can also contact me on my email, and then I'll assist you personally without any charges. Okay. Let's move on to the next question. Let's answer that question. Right. So we're saying Lenz's law, the direction of the induced current or the EMF is always such that it's opposed to change causing it, right? So current opposes direction of rotation. Opposes direction of rotation. Just like that. Okay. And then what else? We know that it actually opposes direction of the magnetic field, right? And then we know that the force opposes the direction of rotation. Remember, this is just Lenz's law, right? And from um, left hand rule, the left hand rule, current flows from rim to axle. That's it. If it still doesn't make sense, just comment the question and they say, please clarify or contact me on the email address that I've provided. All right. Then we have question 7. I partially attempted it. Let me just wrap it out to explain. Okay. Question 7. 4 diodes are used in a bridge rectifier circuit to produce rectification of a sinusoidal AC input voltage In. Fig 7.1 shows part of the circuit, but 3 of the diodes are missing. Alright. The PD across the load resistor R is the output PDV out of the bridge rectifier. State the name of rectification produced by the bridge rectifier. It's full wave rectification. Full wave rectification. Remember, our full wave rectification is like this. The output, you have something like that, right? You lose the negative halves. And then for the full wave, you're going to have that. Like that is your output V. Okay. Part 2. Complete Fig 7.1 by drawing 3 missing diodes correctly connected. Okay, so the way you're supposed, remember this is an alternating voltage. So just based on to approach this question, just assume for the time being this is positive and negative. And you know that current flows from positive to negative, right? So if this is positive, it can't go this direction because it's blocked. Yeah, it can't go here because it is blocked. Okay, so it has to go this direction. And for the way, if it's going this direction, in the direction of the diode should be like that. All right. Okay. And then, so the current goes that way, goes like that. Then it comes all the way. Remember, it can't go back here because this is the positive end. So it has to go from positive to negative. Right? So this is not a positive route, a possible route. So it can't take that route, right? So it goes through here. If it's going through here, that means this diode has to be to the left. Then it comes back and it's to the negative end. That's it. Okay. Now think again. Now it is flipped the direction. Now this is positive and this is negative. So the current moves, it tries to go this way, it can't go, it's blocked. So it takes this path. Therefore, the diode is like that. Then it goes out, comes all the way here, all the way here. Can it take this path? No, it can't take this path. Why? Because it will be going from positive to positive. It's supposed to go from positive to negative. Therefore, it'll go all the way there. And see, it passes right through this diode. Remember, when current comes in from this side, it's blocked. When it's from this side, it's not blocked. Okay. So that's your 4. So all of them are pointing to the left. If your diodes are pointing to the left. right? Part 3. On fig 7.1, to indicate the direction of the current and resistor R. Alright. The direction of the current and resistor R, remember, if this is positive, that goes all the way like that. So the current goes in this direction of the current. And that's it. Good. Now we have V. V in has amplitude V naught and period T. Fig 7.2 shows the variation with time of T, the time T of V in. So this is the sinusoidal wave for the input voltage, right? Since it's an alternating voltage, it's going to have voltage in both directions. That's why it is a negative. There's a negative half cycle and a positive half cycle. Okay. Now here it's saying sketch on fig 7.3, sketch the variation of V out with T between T equal to 0 and T equal to 2T. So what happens here is that since we've rectified the potential in, the EMF in, we no longer have half cycles. These here, we no longer have these, right? So what happens to these? They become positive cycles, so they just reflected up like that. And that is what this graph that I'd already drawn, that is what it is showing. You just reflect in the axis for time, and that would be your answer. Right, that's all you do, and make sure that these here are not sharp. I mean, these peaks here are sharp, they are not smooth. Like, they shouldn't be like this. They should be like that, and then another jump, and then another jump with these sharp troughs. Okay, all right. That's how you get your 3 marks. And then there's this one as well, which I already done. Part 2, the power dissipated in resistor P. Sketch the variation of power at T between T equal to 0 and 2T naught. Alright, so we know that the power is going to be equal to I max and V max, right? That is what the power is going to be equal to. And this is I max and V max. And because we know that our V is an alternating V, alternating potential, right? So our graph of power is going to follow that same pattern, right? It's going to follow the same pattern here that we have here, right? So, and it is going to be it's going to have this shape here. So you mark your points. It will have the same pattern as the V out right there. So as you can see, where your V out is maximum at these points 0 0.5, 1, 1.5, and 2. That is where your power will be maximum as well. 0, 0.5, 1, 1.5, and 2. Right. And then you can label that this is P max, power max. And then the midway, that is going to be the average, P average, just like that. And P average or P mean, whatever term you like to use. Okay. And then this time around, see the difference of these graphs. This one it's sharp the V out, it had sharp troughs. This one is smooth troughs and smooth crests. So the V out one, it had sharp troughs, then it goes again like that. Then this one is different. This one is a sinusoidal wave like that. That's the difference. You need to show the difference for those marks. Okay, part 3. Suggest with a reason how the root mean square value of V out compares with RMS value of VE. Okay, so for this question, really, the power time graph for V in and V out is going to be the same, right? And because it's the same, that will automatically mean that um, the V out and the V in are the same. So if V out and V in are the same, the RMS values are going to be the same because RMS values are both dependent on the maximum V out and maximum V in. And if maximum V in is equal to maximum V out, then the RMS value is going to be the same. Alright. So remember, it's maximum V out. Okay, so it's RMS of V in is equal to V in max, right, over root 2. Remember this formula, right? But V in is equal to V out. So therefore V in max is equal to V in. So we write the V in is equal to V out and V max is equal to sorry V in max equal to V out max, just like that, right? And same power time graph. Without rectification. Remember, we never rectified without rectification, you can include it or not. Therefore, VRMS is equal to VRMS in V in, right? It's RMS V in is going to be equal to RMS of V out, right? Essentially, we are saying that the V out is going to be equal to the V in. Therefore, the V max is going to be equal to the V max in is going to be equal to V max out. So the RMS values are going to be the same. And they have the same power time graph with or without rectification. Alright. Question 8. Figure 8.1 shows the lowest 4 energy levels of an electron in an isolated atom. Right, we have that value right there. So Fig 8.2 shows the lines of the emission spectra of the atom that corresponds to the transitions of the electron from n is equal to 3 and from n equal to 1 to n equal to 1 and from n equal to 4 to n equal to 1, increasing frequency. Alright, remember energy of a photon equals to hf, so E is directly proportional to F. Remember that. So they're showing from n is equal to 3, right? So n is equal to 3, n equal to 1. Okay. That's a large energy change. And then from from n equal to 4 to n equal to 1, then from n equal to 3, n equal to n equal to 1, n equal to 4, n4 to n1, right? So if you look at this increasing frequencies for the light emission spectrum, increasing frequency. So this is definitely going to have n equal to 4, n equal to, is going to have a greater frequency, right? This is going to have a greater frequency than this for transition from n equals to 3 to n equal to 1. Therefore, this n equal to 4 equal n equal to 1 is this one. N from 4 to 1. Then this second one here is n from 3 to 1. Right. Now we want to find for n, you can see from the okay. A. Explain with reference to photons why there's a single frequency of electromagnetic radiation that corresponds to each of these transitions. Okay, so the reason is the fact that energy levels are discrete. Discrete, not continuous. Okay, that means that the only from any difference from any of these energy levels, the difference from it is only one value. So it's not continuous. It's not like pi, which is a continuous number. It's just one. If it's 3.4, negative 3.4 electron volts, then it's negative 3.4 electron volts. It doesn't change. It's not negative 3.41 electron volts. No. Or it's not, I mean, it's not negative 3.411111 with the ones recurring. No, it's discrete. It's not continuous. It's just one value. Okay. Perhaps do you understand the difference between discrete and continuous values? You just search it up on the internet. It will explain to you clearly what is the difference. So energy levels are discrete. So a transition in electron transition emits one photon with a specific frequency corresponding to between two levels. So an electron transition emits one photon specific frequency of energy with a specific frequency of energy, right? Corresponding corresponding to between two levels. right? Okay. Right. So what that means is that when an electron transitions, it emits a photon, right? Um, so let's say it moves from n is equals to 3 to 1, it drops in energy level. It will emit a photon, specific wave frequency. And remember, you can find the energy of that photon, or the energy difference between n is equals to 3 and n is equals to 1, using this equation for the energy of a photon, which is E is equals to hf. All right. And for the second mark, you have to write energy of photon corresponds to exactly 1 frequency of radiation. Actually, you can write it's more precise. You can write that frequency that is emitted, right, of radiation corresponds to the energy of a photon. Okay, right. So B, it says on figure 8.2, draw a line that corresponds to the transition between the electron from n equals to 2 to n equals to 1. Label this line A. Right. So for you to know this, how to do this, you have to look at the diagram again. So we want to draw a line that corresponds to the emission. How do we know whether it's going to be on this side or on this side of the emission spectrum, whether it's going to have the greater frequency or not? Remember, the energy between energy level will tell you um, the frequency. So we want to find for line A, it's an electron transition from n equal to 2 to n equal to 1. So from n equal to 2 to n equal to 1, right? N equal to 2 to n equal to 1. This is what we want. All right. So we know that this is E2, it's E1, right? We know that the energy difference from E2 to E1 is less than the energy difference from E3 to E1 and E4 to E1. Remember, this here, this first one here, first line is the greatest energy difference. So it's from E4 to E1. The energy difference is the greatest. Like even the length, you can just use the length of the lines to determine that. See, the length of the lines from n equals to 4 all the way. This whole line here, first blue line, this one, this line here, that line. Let me change the color so that it's clearer. Change the color. Just put it to green. Right. That green line, it is the greatest energy change. followed by the blue line, right? And then we have the the yellow from n equal to n equal to 1, right? So these are the energy levels that we have, right? So from n is equals to 4 to n equal to 1, greatest energy change, so greatest frequency. Remember, this increasing frequency going to this side, therefore it's that. And then the next frequency from n equal to 3 to n equal to 1, it is this part, n equal to 3 to n equal to 1, this is part, which is E3 to E1, right? Now, the difference, as you can see, the difference in frequency between between the green and the blue line is just this part right here, which I'm shading. So that is why these lines are close to each other, right? It's going to be a different case for n equal to 2 to n equal to 1, because the distance here, this distance is greater. So it's going to be a greater shift in frequency from this line here, from this line E3 to E1. Right? So we're going to indicate that line, which is in red, right? There's going to be a greater shift of frequency, which is at the left, because the frequency is lower to this side. Actually, you could use this triple. It's somewhere here. Right. And then there's even going to be a greater shift in frequency, because remember, E is directly proportional to F. All right. Going to be a greater frequency between n equal to 2 and n equal to 1. Therefore, um, we're going to put this even further out here. Can you see that yellow line? Okay. Right, there we go. Somewhere there, just like that. And you're good to go. That's it. So this is n equal to 2, n equal to 1. This is our line A. And then n equal to 3 to n equal to 2. Um, so this was supposed to be from n equal to 3 to n equal to 2. But still, the gap is small. Therefore, we have our line B right here, just like that. And we are good to go. Right. If this doesn't make sense, comment that question 8B, part 1 and 2 don't make sense, and I'll gladly clarify it for you. See, the frequency of radiation represented by line A is Fa. The frequency of radiation represented by line B is Fb. The energy of the ground state n equals to 1 is E1. Determine an expression in terms of Fa, Fb, E1, Planck's constant, and the energy E3 of level n equals to 3. So what you do is you go for line B. So for line B is what you have. You have E3, the energy difference, minus E2 is equal to FBH. Right, if you go to the diagram, it says E3 minus E2. Well, this is line B. This is line B. and this is line A, right? They then they're saying the frequency here between these two is FB. Then they're also saying the frequency between these two is F. The difference between the frequencies is FA. So you just make your two equations. Then you go for line A. For line A, we have E minus 3. E3 minus E1 equal to FAH. Then when we add them, when you add those two equations, right, we're going to end up cancelling these two out. Then we have E3 minus E1 is equal to FB plus FAH. I just added these two, then factored out the H. Therefore, your E3 will be equal to that. FA plus FB H is E1. Just like this. Right. And that's your answer. I hope that makes sense. Just make your two equations using the energy differences. Right. Okay. Question 9. Define mass defect. So this is the difference between the total mass of the constituent constituent infinitely separate nucleons, right? And the combined mass. So it's literally, so you have the nucleons, right? Before they've been combined into forming the nucleus. When it's been combined to form the nucleus now. The mass difference, remember, some mass is converted when the nucleons, which is the neutrons and the protons, form the nucleus. That is the mass defect. The difference between these two is the mass defect. So it's the difference. The difference between the total mass of the constituent infinitely. Don't forget this word because it shows that they're infinitely separated. There's no initial connection between them at all. Difference between the total mass of the constituent infinitely separate nucleons and the mass of the nucleus. And that's it. Okay. Table 9.1 shows the mass defects of three nuclei. Nucleus, H2, H, that is the deuterium, tritium, and helium. Some of the mass defects there. The nuclear fusion process of a particular star is described by that equation, where X is a particle that has no mass defect. Say the name of particle X, right? It is a neutron. Remember, this is a nuclear fusion. You have that neutron. If you do the mass balances right there, it's a neutron. That is the one that will account for for the one, the total mass. It's a neutron. Show that the energy released when one nucleus of H is formed, each reaction is. Okay. So what you're supposed to do in this case, remember the mass defect. That mass defect is converted to energy from Einstein's equation of relativity. Remember the E is equal to mc squared. So what you can do is you calculate the mass defect first. Right? And the mass defect is going to be mass of He21 minus mass of H of tritium plus mass of deuterium. Right, that's your defect. Therefore, it's 0.030377 minus the combined mass of those two, 0.00238 plus 0.009105. There we go. Then you have that, and your mass defect going to be equal to 0.018884. Remember, this is in atomic units. U, right? Look, it's in mass defect. It's in atomic, unified atomic mass. Unified atomic mass units, right? The U. Okay, so now use that equation. E is equals to m delta. It's delta m c squared. All right. Remember the answer is in joules. Then you multiply your mass defect. We want to convert that mass defect to kgs. So we're going to multiply by U, which is 1.66 by 10 to the negative 27. So if you go to the data booklet, you'll be able to see that value for U, unified atomic mass unit. There it is, 1.66 by 10 to the negative 27. Right. So we multiply that, let's change in our mass by our speed of light, 10 to the 8 squared. Speed of light is given here, 3 by 10 to the 8 squared. When you put that into the calculator, you get to 2 significant figures. Since your 3.8 is to 2 SF. Notice your light, your speed of light, it is to 3 SF. There. It is to, yeah. So answer, you get your 2.8 by 10 to the negative 12 joules as they want it, and you've shown that. So first step, calculate the mass defect, then use the equation E is equal to mc squared. Then you convert your mass defect from unified atomic mass unit U, from that U. Remember that U means unified atomic mass unit. That is what U means, right? And 1 U is equal to 1.6 by 10 to the negative 27 kgs. That's the conversion that you use. So you just multiply by that factor to get it into kgs. Then you multiply by speed of light squared and get your energy. All right. And then part C. The star in B has a radius 2.3 by 10 to the 9 and a luminosity of 1.4 by 10 to the 28 watts. All the energy released from the formation of helium is radiated away from the star. All the energy radiated from the star from the star has been released in the formation of helium. Determine the mass of He produced per unit time by the fusion process. Okay, so what you're supposed to do here first is to calculate the number of atoms produced per unit time. That is the first thing that we're supposed to use to do for this particular question. So to calculate number of atoms per second, so we want atoms per second, right? This luminosity is equal to 1.4 by 10 to the 28 watts. Remember, watts is power. What is power? Power is rate work it done, right? Power is the rate at which work is done. So it's work over time. What are the units for work? Joules per second. So watts can also be written as joules per second, right? So we want number of atoms per second, and we have joules per second, and we also have the energy that is produced by one atom, which is 2.8 by 10 to the negative 12 joules per atom. Remember, we just calculated it right there. It's saying show that when one nucleus, right, is formed, this reaction, that is the energy that is released, but the total radiation released per second, it is 1.4 by 10 to by 10 to the 28 of the entire star. See, so we can use that effect, and it is going to, for mass per second, is going to be 1.4 by 10 to the 28 joules per second divided by 2.8 by 10 to the negative 12 joules per atom or per nucleus, whatever. It says, perhaps let's use nucleus so that you're not confused. Nucleus. Nucleus or per atom. Whatever you use, it works. Okay, nucleus. Right. Right. Then now we have the number of atoms or nucleus per second, right? Now we need to find. We also know that the mass of one atom, right, or nucleus, one atom or nucleus, is equal to 4U, right? Earlier, is equal to 4U. We don't use the mass defect. Because remember, the mass defect is to account for the binding energy. So we are no longer using this table here. So don't even think about this table anymore. Okay. So the mass of one atom is equal to 4U. Since we have the atomic number there, the nuclear number is 4. So that is 4U. So mass of one atom is equal to 4U. And we know that U is the unified atomic mass unit. So just multiply it by 1.66, which is for the value of U, negative 27, to get the mass of an atom, right? Now we want to find the mass per unit time, right? So what we can do now is just multiply this here, the atom or nucleus per second, right? We're going to multiply it with the mass of one atom. so that we get the mass per unit time. All right, and this is equal to kgs, right? Remember, when we do that, we're going to cancel that, and we get our value here. We get it actually as 5.0 by 10. This is the mass per, the number of atoms per second. Okay, by 10 to the 39. Right. Atoms per second. Right. Now, when we multiply it with that, we're going to have 5.0 by 10, 39 multiplied by 4 by 1.66. By 10 to negative 27, right? Then our answer is going to have Q6 fix 3.3 by 10 to 13. Alright, kgs per second. Remember, if you multiply that now by the number of atoms per second, it's going to give us the mass per second. Alright. So it's going to be like mass of atoms per second, which is literally kg atoms per second, which is exactly the same as mass per unit time. Alright. Then that will be your answer. And then surface temperature. We employ the Stefan-Boltzmann law. That is what we employ. And we have the formula, I'm sure, if I'm mistaken, which is pi r squared t to the 4. Right. Then we get rearrange for t, which is equal to the 4th root of the luminosity over 2 pi r squared. Like that. Then we substitute in the values. T to the 4, 1.4 by 10 to the 28 all over over 4 pi squared multiplied by the radius is equal to 2.3 by 10 to the 9. Then you square that. Right. And then there's the constant of proportionality, which is the Boltzmann. Which is the Boltzmann constant. It's here. Right. Stefan Boltzmann constant. There. 5.67 by 10 to the negative 8. Okay. Multiply exactly with that. Right. And then your temperature, final temperature, the true SF is going to be 7,800. Like that. Okay. And last question. Question 10a. X-rays for use in medical diagnosis are produced in an X-ray tube. In the X-ray tube, the charged particles are accelerated towards a metal target by an applied potential difference PD. State and explain. State the name of the charged particles that are accelerated by the applied potential difference. Okay, so in the X-ray tube, we accelerate electrons. So the ones that we accelerate. Okay. Explain how X-rays are produced at the metal target. Okay, so what actually happens is that we have electrons with the filament, and then it is heated And then by the thermionic emission, it's in some form of a tube, something like that. Then we have the target anode right there. This is just half of the diagram. We have the target, right? This is the target right there. And that is just the anode, right? And it's inside a Collie tube. I'm not going to draw everything because it's going to take time. Just look up a Collie tube. Collie tube. And then to show you how the diagram looks like. So the electrons move when they have been accelerated. When they are stopped here, they lose all of that kinetic energy that they have due to abrupt deceleration. That's all of that energy turns becomes is emitted as electromagnetic radiation, which happens to be in the frequency range of the X-rays. That is what happens. That is what happens. And then it goes. These are aluminum filters. If you look up the Cooley tube, everything is explained for this diagram. That is what happens. So that is what we want to write here. So electrons are decelerated uh, decelerated or stopped by the target, right? And their kinetic energy is emitted is electromagnetic radiation that is in the frequency range of X-rays. That's all. And their kinetic energy is emitted as electromagnetic radiation, right? Kinetic energy radiation that is in the frequency of electromagnetic. That is how X-rays are produced. Calculate the minimum wavelength of X-rays produced when a PD with the applied PD is 5.8 kilovolts. All right. So what you do here, you know that the kinetic energy becomes the X-ray photon. For the minimum wavelength possible, remember the energy is equal to CF, which is equal to H, is equal to HF, is equal to HC over lambda. So for this to be minimum, that means energy is to be maximum. So this only happens when the electron gives up all of its energy into one X-ray photon. One X-ray photon with all of the kinetic energy becomes um the energy of the photon. So kinetic energy EK is equal to X-ray photon energy, right? And the kinetic energy in this case, since it is applied by the driving potential, right? The accelerating potential, which is 5.8 kilovolts. Then we use QV for electrical work done, right? In driving those electrons. It's equals to HC over our lambda minimum. Alright, then we rearrange QV over HC. We plug in our values. We have a value for H, 6.63 by 10 to the negative 34, multiplied by 3.00 by 10 to the 8, right, for the speed of light. And then we have the charge. Remember, it's an electron, so the charge of an electron is 1.6 by 10 to the negative 19, multiplied by 5.8 by 10 to the 3. When we do that, we get our answer is 1.4 by 10 to the negative 10 meters. That is the minimum wavelength, so we can get. There we go. Okay. Now, for the last question, B. X-rays pass through a medium that is an attenuation coefficient of 1.4 centimeters per second. Calculate the percent of X-ray energy that is absorbed by 2.8 centimeters thickness of this medium. All right. So, the equation for attenuation is I equal to I naught E negative mu X. I'm not sure if this one is given in the booklet, but usually it's nice for you to know your equations by head, because when you know equations by head, it's just easier to answer. Right? So we want that fraction, right? So remember, this is what is left after attenuation. This is the initial intensity. Initial, right? So we can express this as the fraction by saying what is left over what we had is equal to n e to the negative linear absorption coefficient x is the thickness, right, of the medium. So here we know that we want the percentage that is absorbed, right? So this is the fraction of what is left, right? So the fraction of what we had initially we had I naught. So we can go I naught over I naught. This is the fraction of what we had, which is just 1, right? Then we subtract from that which we lost, right? Which we were left with. This is what we are left with remaining. Remaining energy, right? So we're going to subtract from that using this. That will tell us how much was absorbed. So we know that this is equal to e to the negative mu x, and that is equal to 1. So it's 1 minus e to the negative, and substitute in the values, multiplied by 2.8, just like that. Just like that. And then we have our answer. If you put it in the calculator, it's 1 minus e to the negative 1.4 by 2.8. Right, you have your 0.98. If you express it as a percent, it's 98%. Then you just write 98%. So that's it. We've come to the end of this paper. Thank you for your patience. If you watched from the start, right, all the way through to the end, please consider liking and subscribing to support me and to encourage me to continue to make more past paper solutions like this. I plan to do this paper in just 1 hour in the future, so please consider subscribing. That today I had to explain everything for a special someone who requested this paper. Thank you very much for watching.